The Digital Cellulose Center is a 10-year project financed by Vinnova, industry and academia. These are the partners, 3 academic partners and lots of industrial partners. In this work, we are working with new kind of electronics based on wood. And the vision for the center is to make cellulose-based products an integral part of a sustainable digital society. And cellulose here represents wood. Wood also contains, for example, lignin, and we now include that into the center as well. And we work with 3 value chains, one within energy storage, where we work with new kind of binders for batteries and supercapacitors. We also work with large-scale production in paper machines. So this is an electrode paper made within the center. We also work with medtech and health, so sensors and things associated with medicine and health. We also work with Internet of Things, and that is sensors and communication to different objects. Here you could see humidity sensor directly on wood using wood. And we also work with different carbonization techniques such as this one, including a laser directly on the wood. With us today, let's see if this works. We have Lisa Skedum, and she will talk about PFAS, the new directive, and how that may impact the electronics industry. So please write your questions in the chat, and we will bring them up after 30 minutes presentations by Lisa. And now, Lisa, the floor is yours.
Yes. Okay. So thank you for inviting me to talk about the PFAS today and this coming hour. Can you see the screen, the slides?
We can, yes.
Yes. So the title on this slide basically shows the agenda of my presentation. So I will start giving an introduction to what PFAS is, because maybe not all is aware or have that background. I will talk a little bit about existing and the upcoming PFAS restrictions or the proposal. I will scratch the surface of where PFAS is used in electronics and why. So I will not cover, this is like a massive area, but I will not cover all uses, but you can get a feel for where it's used and where there might be innovation possibilities for you. So that's the plan for the presentation. So if we start with what PFAS is, according to the OECD definition, it's any substance that contains at least one fully fluorinated methyl group, which is 1 carbon with 3 fluorine, or a fully fluorinated methylene group, which is then 1 carbon with 2 fluorine. So that is, if the structure contains that parts, it's a PFAS compound according to the definition. So the 2 substances you can see here are 2 examples of low molecular weight PFAS. It's PFOA and PFOS. They have been widely used for many years, but they have now been they are now regulated in POPs, so they are not used to the same extent anymore. This carbon-fluorine bond is the strongest bond in organic chemistry, and this gives extreme persistence. It's very hard to break those bonds. But at the same time, it's also that strong bond that gives unique properties of PFAS chemicals. And that's the reason why they have been widely used in many different types of products. And there are very many PFAS substances. So I think someone calculated that there are over 10,000 substances. So there are very many. And you can see that for example, for the acids, carboxylic acids, and you have sulfonic acids, and those are kind of the main PFAS chemicals that are analyzed in the environment, and those that are very have been more commonly used. Important to know is that there are also polymeric PFAS, and I will get back to the restriction proposal, but they are also included in the broad PFAS restriction proposal. And with the polymeric PFAS, it means all polymers where you have this fluorine, either in the backbone, as you have for fluoropolymers or perfluoropolyethers, or in the side chain, as you have for the side chain fluorinated polymers. And this latter group is widely used in textile impregnation, for example. So polymeric PFAS is also included in the restriction proposal. The reason why PFAS is such a hot topic, I would say, is that there is a global contamination of PFAS. And this map shows both known and presumptive contamination areas in Europe. And when you get this presentation after today, you can kind of go into the links and you can zoom in on specific areas and you can see what type of contamination, what PFAS levels have been measured, etc. So I just wrote the drinking water directive here, 100 nanogram per liter for 20 PFAS. So that's some kind of a value that you can have in mind when you're looking for different studies where they have measured PFAS in the environment. So you can see the red areas are known contaminations, and the blue ones are more presumptive contaminations. And in Sweden, it's a lot about use of firefighting foams. But another reason why there is a PFAS contamination is because of industrial production of PFAS and products containing PFAS, including the production of fluoropolymers. The big problem with PFAS in the environment is that they are extremely persistent and they don't break down. And it's extremely expensive and challenging to get rid of these chemicals once they have ended up in the environment. So as I said, firefighting foams are one reason for having like local hotspots of PFAS in the environment. But another reason is the production of fluoropolymers. And this is not the most recent study, but it shows that about 80% of the historical emission of this carboxylic acid, perfluorinated carboxylic acid, such as PFOA, are due to the fluoropolymer production. So it's one big reason for emissions of PFAS to the environment. If you want to know more about this industrial contaminations, you can watch this documentary or the Play Movie with our reporters if you haven't watched it already. And there's also a pod on Spotify called Mörkt Vatten, which highlights this fluoropolymer emissions of PFOA in the US, as well as the contamination of drinking water in Kallinge in Blekinge, where they have drinking water contaminated by the military. So once PFAS ends up in the environment, they can end up in our food and in our drinking water, and that is how we are mainly exposed to PFAS. And to some extent also from indoor dust, but it is the release of PFAS into the environment that make us being exposed to PFAS. And since they are persistent, the more we use it, if we have a continuous release of PFAS, that will result in increasing levels and increasing probabilities of both known and unknown effects. So due to studied PFAS, such as PFOA and PFOS, and the negative health effects that have been coupled to that exposure, they are now regulated in the POPs regulation under the Stockholm Convention. And recently also a third PFAS substance, PFHXS, was included. It's both that specific substance, but also the salts and substances that can break down to PFOA and PFHXS that are included in the POPs regulations. So it's more, in practice, it's more than these three compounds that are regulated today. There are also these more long chain carboxylic acids that are included or restricted under REACH. And it's also covers about 200 substances. So there are PFAS restrictions already today. But there is now also this broad PFAS restriction proposal that was prepared by Sweden, Norway, Denmark, Netherlands, and Germany. That there has been a consultation period that ended last Monday. So during 6 months, industry and individuals and organizations have been able to provide feedback on the content of the proposal. But the reason for having this class-wide restriction is that all PFAS are persistent. They do not degrade. Not all PFAS have been studied because it's extremely hard to study substance by substance. But studied PFAS have shown adverse health effects, and many PFAS have similar properties that are worrying. It's impossible to regulate and evaluate substance by substance. It takes a very long time. To avoid regrettable substitution, previously when PFOA got restricted, other PFAS substances were used instead, which show to be as bad as the one that they were substituting. And there are very high costs associated as a result of PFAS exposure in Europe, and there are also extremely high costs associated with cleaning up polluted land and water. And also that PFAS substitution is a major focus in the EU chemical strategy that was published in 2020. So these are the reasons for why we now have a broad PFAS restriction proposal. In the restriction proposal, you are not supposed to have PFAS in products or articles in kind of these concentration limits that are listed here. So 250 ppb for any PFAS, and that's the same limit that exists for PFOA today under the POPs. 250 ppb for the sum of PFAS, and then 50 ppm. This is a much higher concentration, parts per million instead of parts per billion, And this concentration includes polymeric PFAS. So these are good values to kind of have in mind. These levels do not leave room for any intentional added PFAS. So it's not that we can add just a little to kind of get some effect, but these levels are set so that they don't leave room for any intentional added PFAS, but more for some contamination, because we know that PFAS is everywhere, it's in the water, etc. So we can never get zero. This proposal also applies to imported goods and recycled materials. And in the proposal, there are some proposed and potential derogations. And you have the link to the proposal here at the bottom. So I will not go into the derogations now. This is just to show that there was a huge interest in responding to this consultation, and there were more than 5,600 answers. And this will now be checked and evaluated by the RAC and SEAC committees, and they will address relevant evidence-based information in their opinion-making process. So I read somewhere that they are expecting to have something like March 2024. So we'll see. But there are many responses to work with, so we'll see about the timeline. So where do we have PFAS? This is just some, this shows some typically common uses of PFAS. But in many of these types of products, there has been a lot of effort from industry to find alternatives and to develop PFAS-free products. And there are PFAS-free solutions for many of these uses. So as a consumer, when you're buying something like this, ask for PFAS-free alternatives. And these are all uses that have been included in one way or another in the POP3 project that has been coordinated by RISE. So if we move into the topic of PFAS in electronics, common functions, I mean, PFAS are added because they provide a function, hopefully. And one main property is that PFAS provide very good electric isolation properties. So PFAS have very high dielectric strength. So it's very good for isolating electric currents. And there are many materials that may also do that, but since PFAS or fluoropolymers in this case have very high dielectric strength, it's possible to make thinner constructions. PFAS have very high thermal stability, also electrochemical stability, and can withstand high voltages. PFAS is also mentioned for flame retardancy, and the main application, as I've seen there, is that PTFE can be added in the plastic to provide anti-drip properties. So kind of to get the plastic melt in a certain way to avoid spreading of fire. PFAS is also chemically inert. It's provide hydrophobicity, which means that water is repelled, protection against corrosion, and also dirt and oil repellents. So that's very unique for PFAS, that both water and dirt or oil is repelled. So there are not many other substances that provide both those properties. And PFAS may also provide surfactant properties, and which is important for wetting and to create smooth films. So these are some uses, and you can see some products where PFAS, where you may find PFAS. And so if we start with one of the selected uses that I chose, so that is cables that are used to transmit electrical signals or power. And the reason why I use fluoropolymers here is that they have this high dielectric strength and temperature resistance. So therefore they are used in cables. So they are like at the outer layer, closest contact to the metals. And since the cables should withstand the surroundings, you may also find fluoropolymers in the outer jacket of the cable, which is then there to protect against, for example, chemicals, moisture, water, UV light, and to provide flexibility and mechanical protections. It's worth mentioning that there are many cables that do not contain PFAS. So there are other materials that are being used, but it's maybe more in these more harsh conditions where they are really used. So there are other materials with kind of the same dielectric strength, but they melt at lower temperatures compared to the fluoropolymers. So depending on where the cable is going to be used, you will design it to fit that purpose. Another use that has been connected to the use of PFAS is printed circuit boards. And here PTFE may be used. In my investigation, it seems like it's not always used, but it may be used in this core of this PCB board in the laminate. And it seems to be used especially in high-speed, high-frequency technologies, such as wireless communication. So may be used, but not in all printed circuit boards. And you may also find PTFE in the top coat that is added on the circuit board, but it seems to be more common to apply other materials such as urethane or silicone or epoxy as a protective layer on the circuit board. We know that low molecular weight PFAS, if you remember from the first slide, previously it was PFOA and PFOS, but they are not supposed to be used anymore. So now there are other short chain PFAS that is used in the production of semiconductors. And there they have a wide range of different uses, which means that maybe there are leftovers from these low molecular weight PFAS in, for example, the semiconductors in the printed circuit boards, but it doesn't seem that they have a direct function when actually in the final product. But they might end up there because PFAS has been used in the production. And then we have fluoropolymers that seems to be used sometimes in capacitors as well. So in printed circuit boards, you may find PFAS. A third category is batteries, where lithium-ion batteries are common in portable consumer electronics and electronic vehicles. And when it comes to batteries, fluoropolymers such as PVDF and PTFE are used as a binder on the electrodes, as well as in the coating on the separator. And another use not shown here is sealants in the battery to prevent leakage of both the electrolyte, but also from the outside and in. Low molecular weight PFAS may be used in the electrolyte to increase the stability. So it seems that it's a common use, but not all lithium-ion batteries do contain PFAS. And then a fourth example is LCD displays. And here there are more low molecular weight PFAS that are used in one of the sheets to create this dipole, I don't know what's called in English. Yeah, to help align the liquid crystal, and the idea is to improve the optical performance. And these LCD displays you can find in TVs, computers, smartphone watches, etc. And you may also find fluoropolymers on the outer surface as a coating as a kind of anti-fingerprint protective coating that is both dirt and water resistant. So those are 4 different types of, not products, but electronic parts that are used in very many electronic products. I have one last example, but before doing that, I want to just highlight that we, in the POPFRE project, we worked a lot with PFAS analysis and with methods trying to capture polymeric PFAS. And here we use a combination of quantification of total fluorine with combustion ion chromatography, and then if we measure more than 50 parts per million, if you remember from the restriction proposal, then we can verify if the source of fluorine is actually PFAS. So then with pyrolysis GCMS, we can get more structural information and verify that the fluorine comes from PFAS. Just a side comment is that if you test for halogens, I mean, that's a quite common test commercially. They only include chlorine and bromide. So if you get like a halogen-free report, it may not indicate that it does not contain fluorine. So just a comment. But then when doing this analysis in different types of products, we could find PTFE in construction plastic. So we analyzed, this graph shows results from this kind of wireless headphone cases, 2 different ones, and also the plastic of a loudspeaker. You can see that the total fluorine concentration in this PC-ABS plastic was between up to 2000 ppm. And the restriction limit is 50 ppm. And in this case, we could then verify that this fluorine actually comes from PTFE with pyrolysis GCMS. And this shows this other use of adding PTFE as a flame retardant or anti-drip agent in plastic. By doing these types of analysis, we also found that you may find inorganic fluorine in electronic products. So in this case, we took apart the coffee maker and we analyzed different parts you can see like that you have this kind of heat protective sheet, and you have a coating close to the heating source. And here we also measure quite high amounts of fluorine, but we could not verify it with pyrolysis GCMS. And with some more further investigation, we found that this is mica, and mica is a pigment that you can add for heat and fire protection in high temperature applications. And we know that it also can be used in cables. But it shows that if you don't know if you have PFAS, there's also a possibility to analyze and see if you find PFAS in your products. So we talked about production of PFAS and where it's used. So when products are entering or coming, have been used and they don't work anymore, you are working with, they are ending up as waste. And we know that PFAS from discarded products and materials can end up in landfill leachate. And here, for example, PFBS has been connected to electronic waste. And incineration of PFAS can release air pollutants and greenhouse gases. And there's a lot of ongoing research here, like what's happening with PFAS in products during incineration. And where does the PFAS end up in what type of PFAS is formed. But it's also the waste handling may lead to PFAS emissions into the environment. And if we think of recycling and using material to other products, it's difficult to separate PFAS from material flows. And it's also like if you have a product like this, how do you know which parts to take out to remove the PFAS to be able to use the rest, for example? Or can you use PFAS and PTF in plastic to other products using that plastic? Then you may end up with PFAS in products that are intended to be PFAS free, but if you have used recycled waste flows and waste streams, you may get PFAS in those products anyway. So I'm approaching the end here. I just want to move more into like some substitution work. And one thing that many people or many companies ask is, do we have PFAS in our products? Because there are actually, since many of the production happens in Asia, and you get articles from suppliers and you don't really know the chemical content. This is kind of where many companies are at the moment. So in order to find out, you can start with checking what internal knowledge do we have within the organization. There are many, probably a lot of information already internally. Ask suppliers, and here it's good to remember that safety data sheets does not provide information about PFAS. So you have to ask specifically for PFAS content and be clear that you mean all PFAS, also the fluoropolymers, even if they are not regulated today. You can evaluate the function that your products has or parts of products have, and evaluate where is it likely that we have PFAS. And then you can think of the functions that PFAS usually provides is water repellents, dirt repellents, low friction, non-stick, forming smooth films, isolation, corrosion resistant, chemical resistant, and high temperature applications. So if you have any of these functions in your products, you may have PFAS. So that's kind of where you also way to start. Chemsec has a PFAS guide where they kind of add information about PFAS in different types of products that you can look. There's a link here. And you can also do PFAS analysis. And here we have the methods developed within the POP3 industry project, where we have methods that work also for polymeric PFAS, first quantification and then verification. So the practical phase-out work, ask, is PFAS really needed in my application? We have seen examples where you have kind of asked suppliers, like, do you really need this? And sometimes they say, no, we don't really need this, we can use this instead. And there has been a switch. Request PFAS-free solutions from suppliers. Collaborate within the supply chain and with other partners. You can do it collaborate in different forms. You can also think new designs to avoid PFAS. There is a link here to an article showing how Marshall has worked with designing away from PFAS. We know that legislation and regulation boost innovation. So a lot of things will happen this coming years. And start now, like even if you would have a time-limited exception in the when it comes to time-limited derogation, when it comes to continued use of PFAS, we know it takes time. So start now. Final slide. There are definitely possibilities for future innovations. There are alternatives for many uses in electronics available. But we also see that there are new innovations, uses where new innovations and solutions are needed. And I listed a couple of them. So this construction plastic seemed to be some kind of some unnecessary use of PTFE to get kind of the correct anti-dripping properties to pass certification. So I think this is one important solution or use. Chemicals and materials for very harsh environments. There seem to be less alternatives there. Process chemicals for semiconductor industry, as well as the batteries, and it seems to be the cathode electron binder that seems to have more challenges with alternatives, according to this manuscript in progress by colleagues. So green electronics has a bright future, not least because of the PFAS, but I guess also from a general perspective of moving into more bio-based renewable sourcing. And important to consider the life cycle, because as for PFAS, we see that there are concerns with production, there are concerns with the end of life, some concerns with the use phase. So it's important to consider the whole life cycle when you develop new materials and consider all the chemicals that are used in the process, etc. To get the safest and most sustainable material in the end that also provides function. If you want to collaborate, don't hesitate to call or contact Hjalmar Granberg if you want to work with innovations and new possibilities. And don't hesitate to call me or contact me if you want to know more about PFAS and those uses and PFAS analysis.